first question you probably have about our project is, what is the problem we're trying to solve? Imagine spending a single day without using your smartphone. It would be pretty hard, right? They've become an essential part of our lives. We use them for email, watching videos, playing games, and some emerging technologies such as virtual reality, Internet of Things, and machine-to-machine communications. All of this requires new methodologies for wireless transfer of, keyword being, big data. Let's think about how your smartphone works. Your smartphone transmits and receives data from a base station. A base station forwards your data to the person you're calling or the website you're trying to access via the mobile carrier network. Let's say the base station is trying to send data to your phone, which is in the form of binary. Let's say we're sending 01101. By the time the data goes through the air, through buildings and other interferences, your phone might actually receive the wrong data. So not only do we want to transfer big data, we want to transfer it accurately. Our project is about polar coding. Before we talk about polar coding, let's look at what is channel coding. Let's go back and look at the transmitter and receiver model. We also have a transmission channel, which is typically the air and the environment. Let's say we're transmitting data, in binary of course. Let's say we're transmitting 010. This is the raw data, which is referred to as the uncoded data. We can code this by adding more bits to it. We get 010, 010, and this is the coded data. The takeaway is that coding adds more bits to make the transmission more robust to disturbances on the channel. To understand channel coding better, let's think of each bit that is transmitted as a fish in a bowl. In a typical coding scheme such as turbo coding, we can think of each bit that is transmitted as a bowl of fish that is half full of water. As this goes through the transmission channel, due to noise and interference, some of that water will spill out. Depending on how much water spills out, you might end up with a bowl that has less than half the amount of water, or with very little water. This signifies how your data is transmitted. So depending on the magnitude of the interference on the channel, the fish could be dead on arrival. So how is polar coding different from other coding schemes? Let's take a look at the fishbowl example again. We have two bowls of fish that are half full of water. We can transform these two bowls of fish using a matrix, known as Archon's kernel. With the transformation, we can get one bowl of fish that is full of water, which means that the fish has a very high likelihood of surviving, and one bowl of fish with very little water. Polar codes can transform an average quality channel into either a really good channel or a really bad channel, hence the name polar codes. We can transform this to an n number of channels, so we can have n number of average quality channels, and we can make some of them really good and some of them really bad. So the advantage of polar coding is we know which channels are really good, and we can choose to transmit the data that we want to send only on those channels and not any on the bad channels. This leads to something called the Shannon capacity. Shannon capacity is defined as the maximum rate at which information can be transmitted over a communication channel without error. This is what makes polar coding so advantageous over turbo coding and LDPC. Let's take a look at our implementation of polar codes and all the bright ideas we came up with to optimize it. We implemented the list successive cancellation polar coding. Some of the optimizations we did: we subdivided the transfer block into smaller blocks, as polar coding only supports 2 to the n number of bits per block. We made it compliant with the LTE OFDM modem. We implemented the CRC block and optimized the design around a specific design SNR value. We also implemented in hardware using Vivado HLS. This is a MATLAB simulation plot that compares polar coding versus turbo coding. Y-axis is the bit error rate, x-axis is the signal-to-noise ratio. If we look at polar coding, we can see that it gets better at higher SNR values compared to turbo coding. This is our hardware setup. So we're transmitting an image on the transmitter using an OFDM LTE modem, and it's going to the receiver. Both the receiver and transmitter are Z boards with two analog devices, RF cards. We can see that the image is being received. This is the constellation diagram of each burst that's being received, and here we see that the image is recovered. This is the data taken on the actual hardware. On the y-axis is bit error rate, x-axis is SNR. You can see the orange line, which is our implementation of polar coding, performs better than the turbo coding, which matches the software simulation plots from earlier.